hydrogen-powered jets for zero-carbon travel, vertical takeoff taxis for traffic-clogged cities, hypersonic flights from London to Sydney in under 2 hours. Flight is being reimagined for our changing planet. Let's speak to the people leading that transformation. I'm Caroline Steele. Welcome to The Engineers. I'm with 3 world leaders in the field of aircraft engineering and an audience at the Royal Geographical Society in London. Now, let me introduce our engineers. Kelly Latimer is from the US. She's been on the front line of aeronautical engineering as an experimental test pilot for NASA and Boeing, and also as director of flight test at Virgin Galactic, and she is now president of the Society of Experimental Test Pilots. Daniel Mochi-Glover is from Brazil. He started his career as a chemical engineer, but has since become president and CEO of Embraer X, which is the innovation arm of the world's 3rd largest aircraft manufacturer. And Rob Miller is from here in the UK. He's director of the Whittle Laboratory and professor of aerothermal technology at the University of Cambridge. He is also director of the Rolls-Royce Whittle University Technology Centre. Please join me in welcoming them all. Kelly, we need to talk about spaceflight. So you joined Virgin Galactic in 2014, and they have a really unique way of launching spacecraft. So there's a mothership, which to me basically looks like 2 planes sort of stuck together with their wingtips stuck together, and then sitting in between them is a spacecraft that somehow gets launched into space. How does that work?
So the mothership E basically is 2 fuselages, and everybody always asks, do the pilots sit in different fuselages? And no, we all sit in the right fuselage. So the left fuselage is basically empty. It's just there for aerodynamic and mass symmetry. The mothership takes off from a runway, so that was one of the really cool concepts of this, was you could make this operation anywhere you want in the world. You don't have to build a vertical launch. You don't have to have any of that infrastructure. You can just do it off of a runway. So anyways, the mothership takes off from the runway, climbs up to about 40,000 feet, just drops the spaceship straight down. And this point, the spaceship is about half the weight of the mothership. So I flew the mothership too, from dropping the spaceship, as soon as you let it go, you immediately get a 2G jump in the air in the mothership. It is awesome. And there's this big thing, so you turn off to the side, the spaceship drops, so the pilot goes full forward just to get a good separation. We come back, and then you say fire, and the pilot in the right seat fires the rocket motor, and it is the most absolutely insane acceleration. It is 70,000 pounds of thrust within about a second.
Wow.
So, 1 G is like the force of gravity sitting here. It's 3.5 G's acceleration that way.
So you must feel like you're sort of being pressed into
Exactly. Crazy acceleration. The vehicle accelerates, basically goes transonic, supersonic. Just on the other side of supersonic, we run the stabilators, pull the aircraft straight up 80, 90 degrees. The rocket motor is still burning. We're still 70,000 pounds of thrust going straight up. And as we're burning fuel, we're getting lighter. So our acceleration is increasing. So it is like being shot out of a gun, out of the atmosphere. So you're just accelerating all the way up. The whole world just goes to black void. Then after 1 minute, and the rocket motor only burns for 1 minute, but that's all you need. That's enough to get you well out of the atmosphere and up to about 55 miles. The rocket motor shuts off. It goes 0 gravity. Everybody in the back unstraps. There's windows all across the top. And then the pilots up front, we feather the vehicle. So essentially we fold those booms. So the vehicle kind of folds into a 90 degrees. So the 2 booms in the back fold up 90 degrees. And when that happens, the vehicle rotates around, and you get the full view of the planet coming into view through the overhead windows, and it's absolutely stunning.
Thanks, Kelly. So, Daniel, we're going to go from space to much, much closer to home.
Low altitude now.
Low altitude, exactly. So I'm sure many listeners in our audience here in the room will agree traffic in cities can be a real problem. Your solution to that is the electric flying taxi, or an eVTOL, which stands for Electric Vertical Takeoff and Landing.
Exactly.
Some people might say, well, we have helicopters. What is it that eVTOLs can do that helicopters can't?
Helicopters, they can perform the mission, but they have a few shortcomings. Number one, they are very, very inefficient from a power, energy consumption perspective. So it takes a huge energy just to keep a helicopter hovering in the skies. So you add energy costs, maintenance costs, it becomes a very, very costly solution. Besides, it's very, very noisy.
Yes.
So when we launched Embraer X, that was one of the first problems that we dedicated our attention to, exactly because urban population is increasing all over the world. So traffic is becoming a terrible problem. So why not explore the third dimension? This low altitude economy, could there be an answer there?
So they don't use jet engines, but instead you have sort of 8 horizontally rotating blades which lift the vehicle, and then 1 vertically rotating blade which drives the vehicle forward. Why did you go for that design?
And the wings.
And the wings.
Don't forget the wings, because they are
Key, otherwise
they're
it might go
key.
down.
Yes, yes.
You can tell I don't design them.
They are key to beat the helicopter, as I was explaining before. So the 8 rotor lifters, they will allow us to take off in a very similar way, exploring the same phenomena that would lift a helicopter. But because it's a multi-copter, it's much more, we have the redundancy. So the level of safety is much, much higher. And then when we get to the cruise altitude, only by then we'll turn on the pusher, the horizontal rotor that will start pushing the aircraft forward.
And by redundancy, you mean if one of the engine fails, you've got built-in sort of backup.
Exactly. Going back to the wings, right? When we turn on the pusher, it will start pushing the vehicle forward, and as it accelerates and gains more speed, there will be a transition to what we call the wing-sustained flight, the wing-borne flight. And then we turn off the 8 lifters because they are no longer needed.
I mean, I'm just picturing trying to
The
fly
helicopter
this.
becomes a fixed-wing aircraft at that moment.
But how do you not, so say I'm the pilot, you're going up, you've got your 8 rotating horizontal blades, you have to turn them off. I guess they need to stop in an exact formation, otherwise it's going to be quite chaotic. Then you have to turn on your forward driving blade. How do you not stall? I'm sure I would instantly stall.
It is a great question, and the only reason we can do it in a very safe and smooth manner is the latest generation full fly-by-wire technology. So it's a computer and software.
Now, Rob, you're working on a cryogenic jet engine, which sounds super cool. Thank you. Can you walk us through it? What exactly is it?
So you may have heard that people talking about cryogenic hydrogen. So by cryogenic, I mean you cool it down to the point where it actually becomes a liquid, and then you store it on board the plane as a liquid. But what we started to realize just around the start of COVID was that as you liquefy these gases, effectively what you do is you store energy in them like a battery. And there's a new type of jet engine, really the first shift since Frank Whittle's original engine, which allows you to extract this as you expand it back out in the engine. And we calculated at the time, I remember we did a first analysis of the engine and we got about 10% improvement. That's 10% less energy to fly than any jet engine has flown before. And then we worked out theoretically 30% was possible, which is like just an incredible number. 30% less energy to fly than any aircraft engine that has ever flown before. And we set up this mission team, and the team's been working for about 1.5 years, 2 years, and there's now 9 patents.
That's incredible. And if you think about rolling out planes with cryogenic engines in airports like, say, Heathrow in London, how would Heathrow need to change? Because you've got to be able to get this fuel down to an incredibly low temperature. Yeah. What kind of changes would you need to make?
So the really important thing here is the 20 largest hub airports in the world are responsible for half of aviation's fuel burn. Now, changing 20 structures in the world compared to changing all the airports in the world is doable.
It's better,
so you
yeah.
could decide, if you took strategic hubs and you converted those to cryogenic systems, you could, I think that's probably the fastest way of making that conversion happen.
Thank you, Rob. So, Daniel, if your eVTOLs get to the point where the tech is 100% there, they're ready to go, cities aren't built for them at the moment, right? So you're also going to have to think about infrastructure changes. How will cities need to change to incorporate eVTOLs?
Absolutely. The good news for the start of operations is that the eVTOLs can start operating from existing heliports, helipads, airports. It's going to be a limited operation, not as many routes, but that's a good way to get started. As we progress, what we will need is to convert more locations to vertiports, which means bring the electrical infrastructure, the fast chargers. The other major challenge, as was asked before, is related to the air traffic management. We're putting a lot of investment on that aspect because this will really make the difference to allow that ecosystem to scale in the big cities.
Do you think it's likely eVTOLs will be used to, say, shuttle people from a city center out to an airport?
To an international airport.
Yeah.
That's one of the very first use cases that we see. Other use cases are like air ambulances or taking care of medical emergencies where the time you will save may imply in saving lives as well. So we'll start with few cities, few routes, and we're talking 3-4 years from now. It's not a distant future.
Great, thank you, Daniel. So, Kelly, back to you. You have been incredibly important in super high-speed suborbital flight, and we're now hearing conversations about hypersonic passenger flights where people might be able to go from London to Sydney in under 2 hours. I mean, that sounds almost impossible. What's the idea behind it? What's the engineering?
Well, I mean, so one thing is you could do a suborbital flight, because Virgin Galactic had talked about that, where instead of the suborbital flight going straight up and down, you basically do it point to point. But if you think about it, the vehicles we have now, even hypersonic vehicles after they do a test, or space vehicles when they come back in, they're essentially projectiles. So when you come back in and re-enter, there isn't an engine, there's no holding pattern, there's no waiting for the runway to clear. I mean, you're coming down and you're not going to stop. So. And so if it's vertical, one challenge is, Starship would be capable of that, right? But you need to have the whole landing and the catching mechanism and that type stuff. Or if we come back in like a glider, it's not going to be at Chicago O'Hare. You're not going to come in clear the runway, everybody stand by, we got to land. But you certainly could do it, so if you pick a spot that's in the middle of nowhere and then you combine it with eVTOL, you can actually have those fast flights, land someplace, but to have the technology to still have an engine that can go from the ground to hypersonic, back down to subsonic, and land again is really, really challenging.
So hypersonic is moving at faster than the speed of sound. Subsonic is slower than the speed of sound.
Yeah.
Your average passenger jet is...
Hypersonic is very fast. So supersonic is, up to about Mach 3 or so, and then hypersonic is when you're above Mach 3 and Mach 5.
And Mach 3 is 3 times higher than the speed of sound. And an average passenger jet is that like 0.8?
0.8, yeah, about 0.8.
Of the speed of sound? Mm-hmm. Okay, so this is, a hugely different way of traveling. But there's a world in which you could go up, go sort of do a quick suborbital flight, come down, land maybe in the middle of an Australian desert, jump on one of Daniel's eVTOLs, go to the center of Sydney, and maybe do that in 4 hours?
Yeah, see that, and it actually is possible to do it with, and not have to be like a vertical where you could actually have a runway and do it where you come in as a glider.
I guess one of the key things that might make this possible is that at higher altitudes, the air is thinner, there's less resistance, you can travel faster, you can use less fuel, is that right?
Yeah, because once you have enough, it's all about getting the energy to get you out of the atmosphere. Then once you're out, it's pretty much a free ride.
So, Rob, your lab defines itself as a global center for net zero aviation and energy. Cryogenic engines, super exciting. We're not quite there yet. They haven't been rolled out yet. Is there anything that airlines or passengers could do right now to reduce the environmental impact of flying?
Yes, I think what a lot of people don't understand is that half the climate impact of aviation is not the burning of the fuel, it's the clouds, the contrails that form. So basically 1 in 20, the white lines behind planes don't do any damage, but 1 in 20 flights travels through an area of airspace called ice supersaturated, about to grow a cloud. That cloud grows, it lasts for sort of 6-9 hours, and we know, you know that at night, if it's cloudy, it feels warmer, and if it's clear sky, it feels colder. And that's because the cloud's like a blanket, keeping in the heat to the Earth. And those clouds, that 1 in 20 flight, the cloud over 6 to 9 hours does the same warming of the planet, we think, though the uncertainty is relatively high, as the CO2 from all 20 flights do over 100 years.
What? Okay, wait, so in that very short time period, you're having the same effect as all of those flights over 100 years?
Yeah, but now this is a real benefit because the areas that form those clouds are like thin pancakes. And therefore, if you knew you were in one and you changed the altitude of the plane, you could switch off that cloud formation. And so this is something that we think you could tackle relatively simply. Hopefully, you will see in the next year or so the first large-scale trials going off, and hopefully the UK will be leading those trials. But this is a real opportunity over the next 5 to 10 years to have a big impact.
My final question, which is for all of you. So we've talked about suborbital flight, eVTOLs, cryogenic jet engines, all really exciting. But if you think about the future of flight in the next 30 or 40 years, what do you realistically think it will look like? What changes do you think we will actually see? So yeah, let's start with you, Rob.
Okay, so the big challenge over 30 to 40 years is that at the moment, the way we're decarbonizing flight is we're talking about sustainable aviation fuel. And sustainable aviation fuel is making a replacement from jet fuel out of effectively waste biomass. Now, if you scale that up to 2050, 60, you're pretty much using half of the world's waste biomass for aviation. It just becomes an unsustainable problem. And therefore, if we're going to decarbonize aviation, not thinking about the difficulty in the shorter term, if you're thinking about 2050 to 2060, you have to get carbon out of the cycle. And really, hydrogen is one way of doing that.
And Kelly, what do you think? What do you think we're going to see in our skies in 30 to 40 years?
So I think in the near future, we're going to see the return of supersonic commercial flights. I think there's a big push for that now. NASA has a program with the Quiet Boom X-59, so they're demonstrating Quiet Boom technology. FAA, due to this, is going back and kind of look at those changes. So I think that's one thing that we're going to see as far as getting faster. We're going to see that jump back into supersonic flights.
So commercial passenger jets being able to go faster than the speed of sound, like the
Yep.
Concorde
Yep.
used to.
Yeah. And I think we'll see that, and it used to be just over water, but I think we'll actually see that change and be over land as well, which is a huge opening to the market. Yeah, there's other technologies out there, like flying wing has been there for a long time, and there's actually companies that are involved in doing that. NASA's looking at a potential X-plane for that. But
So
that's
that
where
sort of
it's-
looks like
it's like a
just a
big
giant
delta.
wing, and people sit inside the wings. There's no
Yep.
kind of tube with wings. It's just a
Yep.
big flying triangle.
Yep, exactly, and it's about
Landed wing body.
about 30% more efficient than with the fuselage wing. So new interior though, so you're gonna have some little cameras that are just showing a picture of stuff and not actually looking out the window.
And Daniel, what about you? What do you think? 30 to 40 years, what are we realistically going to see in our skies?
The eVTOL has been teaching us how to deal with a full electric aircraft, how to deal with high voltage systems on board the aircraft, battery systems, battery management systems. It's a whole new world that is opening up, but still is a first step. What we see in the time frame that you described is for shorter haul. I mean, the eVTOL will cover a very short distance inside the city. But maybe connecting cities that are not that far from each other, we'll start seeing hybrid electric solutions or hydrogen fuel cell. We'll eventually get to hydrogen being burned in the turbine. We'll have to see sustainable aviation fuel as a transition.
Yeah.
So we
Rob
can...
looks like he wants to jump
very
in.
briefly.
Yeah, go for it.
So I think one certainty over the next 20, 30 years is it's going to be an incredibly exciting domain
that's for
to
sure.
work in, and I wish I was younger.
So you could.
Well said. Extremely well said. And the
Thank you.
configurations that Kelly mentioned, the blended wing body and other examples, for a very, very long time, we've been used to think of an airplane as the tube and the wings.
Yes, it's hard to picture a flying
It's hard
triangle.
to picture something different, right?
Yeah.
The eVTOL is already something
Pretty
very
different.
pretty
Yeah.
different. The blended wing body is another example. What other examples of configurations, novel configurations, may come up from the brilliant minds of the young engineers who are still about to join our industry and that are probably more welcome to do so right now than in any other time
Yeah.
in the last decade. So it will be indeed a very exciting time.
Thank you. This is the engineers flying at the edge from the BBC World Service. Who has a question for our panelists? If we go to, I think, the person who's directly in front of you there, and then if we come to the person here. Thank you.
Hello, my name's Sandy Millen. You mentioned quite a few different fuel sources, but nobody said anything about solar. Will solar have any role in the future of aviation at all?
Good question. Rob, do you want to take this one?
Yeah, I'm happy to say that. So the power density involved in solar is just not sufficient to do anything more. So you might well get communication systems that can be put up at high altitude or monitoring of ground for environmental reasons, but there isn't just the power density, I'm afraid. Batteries will take you a certain distance, but ultimately some form of fuel. And really just the one choice in chemical fuel you have to make is jet fuel at the moment, or we know it as dinosaur juice,
There is lots of energy.
an incredibly complex molecule. And making complex molecules is hard. You want a way of making a simple molecule, CH4, methane, or H2. They're the ways we're going to scale fuel production.
Great, thank you, Rob. And we had a question over here.
First of all, thank you all very much. It's fascinating. I began in the aviation industry in 1969 with BOAC. The key thing about aviation is that it runs for profit. How are you going to ensure that your technology meets, actually goes into service sustainably?
I think maybe this is one for you, Daniel.
Aviation is a very thin margin industry, as you certainly recall. So it's a big challenge when we talk about sustainable aviation fuels, when we talk about even liquefied hydrogen. Or today, it seems like very hard to make them comparable on a price basis. But as society, we need to be asking ourselves the question, how do we price the carbon-based fuels, the dinosaur juice? How do we want to split or share that cost when we deploy new technology?
So I think you've hit the big problem. No aircraft ever launched which isn't at least a 10% better value proposition than the incumbent aircraft has ever succeeded since the start of aviation. And virtually all the routes to net zero are about 30% more expensive. So you've got to tax in some way if you want to get that transition. There is one route which breaks that rule, and that is the route to green methane. So if you had an aircraft today that ran on liquid natural gas, it would be cheaper to operate in the United States by about 10% than a current aircraft. Once you've done that, you've got a cryogenic system in operation, and then you would start to scale into green methane. And the green methane is going to be scaled because Musk is scaling green methane in California for the Mars missions. And the reason he's doing that is because CH4 is super easy to make. It's not dinosaur juice, it's cow farts. It's the Sabatier process, and they're going to fly the plants to Mars and build the fuel to come back. So California will be awash with green methane. So there is a route there that is practical and cheaper, but it is the only one. The rest are all more expensive.
Let's go for this person in the very front.
So we've seen driverless cars come onto our streets. Do you think in the future we will see flightless or pilotless aircraft?
Sadly, yes.
Kelly's
Yes,
like, my
but in a
job.
much more
Yeah.
excited way.
Yes, yeah. I would say that there's a huge, I mean, we talk about the future. The future is, and there's a question about automation. The future is more automation, more autonomy. I mean, artificial intelligence, co-pilots. I mean, that's the future. So, yes, I think you would never have a commercial flight with a lot of people without anybody who's monitoring, but it may just be one person. But absolutely, that's the future.
For the
Sad
e-vehicles, is part of the design. So we pragmatically believe we'll start operating with the pilot on board. But again, in order to scale up that industry, pretty much all players are assuming it will be autonomous.
Okay, so we need to get ready for flights without pilots. Sounds absolutely terrifying.
And I will remind you, for those in this room who are about my age, elevators use it to have pilots.
So it's a good point. There were elevator operators, that's true.
We're not missing them.
Yeah. That's it for the engineers flying at the edge at the Royal Geographical Society in London. Thanks to our brilliant engineers, our audience here, and to you, wherever you're watching, all around the world.